So let's go and get started. I'm going to start off by apologizing to the folks in the room that are also taking structural analysis because, yeah, this is going to get a little redundant. Enjoy the coffee. You'll be all right. I am going to show you a few different things that you didn't learn in structural analysis. And I'm probably going to edit some stuff in structural analysis later to take out some of the material that crosses over. Okay, so what we're going to talk about today, and probably next time, whenever that is, which I guess will be not Thursday, but the following Thursday after the exam, is the idea of computing beam deflections. Now, we're focusing on beam deflections because we've sort of handled the deflection of everything else. You know, if I have a bar that's being yanked on, I can determine its deflection, PL over EA. If I have a bar that's being twisted, I can determine its total rotation, TL over GJ. We figured that stuff out. Beams are a little different because the loading and the distribution of load and stress is a little more complicated. Determining beam deflections themselves are a little more complicated. And if you take a course in structural analysis and you just open up the book, you know, for structural analysis, you'll find that there's a litany of different methods that you can use to compute beam deflection, and they all have their advantages, disadvantages, and what have you. I try and do my best when I teach the course to zero in on the methods that I believe are the most important and the most versatile, but there are different methods for different applications. Some of them are better than others. What I'm going to do for you all, since I believe that this is somewhat of an introductory course into structural mechanics, I'm going to show you two methods. One of them is going to be double integration, which is directly solving the fundamental differential equation for beams. Don't worry, this isn't going to be a differential equations method. Anybody who's had DiffEq, we're not going to be writing characteristic equations and doing exponentials or Laplace transforms or anything like that. It's not like that, but there is a differential equation associated with beams that we do need to discuss. That's going to be method one. Method two is going to be superposition. In other words, a lot of very basic bending and deflection formulas for beam loadings are easy to find. Go to Google, and they're all over the place. So the idea is if I know the deflection due to this load, and I know the deflection due to this load, if I want to find the deflection due to both of them, just add them up. So that's where superposition is going to come into play. But you got to be careful and make sure you're doing things correctly, make sure that your units make sense, and all that. All right, sound good? All right. So in order for us to assess beam deflection, we're going to have to determine what is the relationship between the forces that we apply to beams, namely bending moment, and we're going to have to determine that relationship between the moments and the resulting deflections. So in order to do that, I'm going to make some assumptions right off the bat. Now, my first assumption is that the behavior is going to be linear and elastic, which I got to believe is pretty a reasonable assumption given the nature of what we've been doing this semester. Just about every type of problem that we've been assessing this semester, we assume that the behavior is linear and elastic, which is more often than not what we would desire anyways. I mean, I would prefer dealing with linear elastic behavior as opposed to yielding when I can help it, you know, from an analysis standpoint. It's easier to deal with stuff. Another assumption that we're going to make is that deflections are small. Now, that might not make a whole lot of sense. What do you mean deflections are small? The easiest way I can describe that is to present you the following example. So let's say that I'm standing on top of a big hill, okay? All right, and you know, let's say Mr. Batiste doesn't like me very much, and he decides to give me a nice shove, okay? Now, he shoves me, I might be able to catch myself, maybe, you know, considering hopefully he doesn't shove me too hard, okay? Now, let's take that same example, but let's say I'm wearing an 80-pound backpack. Now, I'm not that strong, this doesn't have 80 pounds in it, but let's, you know, illustrate that for a second. Now, if he does the same thing, I propose to you it's going to be harder for me to stand up, okay, or to stay upright. Why is that? Well, here I am, I'm standing, and as soon as he pushes me, what happens? I go like this a little bit, right? So the backpack, here's the backpack, right? And he pushes me, that backpack is now off center. Make sense? So if that backpack's off center, I propose it's causing a bending moment about my center line, right? The load times the distance. That bending moment is going to cause more deflection, which is going to cause more moment, which is going to cause more deflection, which is going to cause more moment. See how it builds up? See how it builds on itself? That's what's called a second order effect. When we're dealing with second order effects, we sort of treat those as quote unquote large deflections. I'm saying that for beam deflections, the deflections are so small that we don't have to worry about that. I mean, here I am, I'm sitting on this table. I propose to you it is deflecting, but the deflections are very, very small. We don't have to look at equilibrium of the structure once it's displaced. We can treat them both as the same. Make sense? All right. Do we deal with second order deflections in real life? Yeah, we do. And there are instances where we do have to deal with it. A very common example, and I'm sorry, I'm a civil engineer, this is what I relate stuff to, but a very common example is to design the lateral system in a building, okay? If I take this building, most of the building has been designed to withstand gravity forces, things like dead load, things like live load, things like snow, stuff that acts up and down, right? I'm a person loading this building in an up and down fashion. You know, I'm not pushing on it like this, okay? There are two force effects in the world of structural engineering that act laterally. Two big ones. One of them is wind, acting like this. Another is earthquakes. Earthquakes they don't really load a building, they accelerate a building in this direction. Make sense? Okay. Those columns that are part of that, and those elements that are part of that lateral system, which we don't design the whole building for that, we pick a small component of it, are being loaded up and down, and they're also being loaded in this fashion. And those elements are a lot like the guy on top of the hill with the heavy backpack, because they're having to hold the building up, but they're also having to hold back the wind. You see what I mean? So they experience those second order effects that we have to account for. Now, in the world of steel design and concrete design, we have some approximate methods that we can use to address that, but that's really more of a, you know, design-specific related topic for another day. But I just want to make sure you all understand what I'm talking about. Sound good? For now, we'll neglect that. We can tackle that stuff later. Okay. All right. So I propose that based on those assumptions, let's take a chunk of a beam. You know, we'll say it's some length L, and let's look at it once it's deflected. And I propose it looks something like this. Now, on this deflected shape, I've got this solid line here representing the neutral axis. That's where the centroid is. And by now, we should have a pretty good understanding of what that means, right? It's where sum of AY over sum of A, that's where the centroid is. Now, I propose that when we deflect a beam, because of our assumptions, the neutral axis stays the same length. In other words, if that beam was 10 inches long, after it has deflected, the length of that neutral axis, the length of that curve, it's still 10 inches. But I propose that the deformation has occurred above and below that line. For instance, everything above the neutral axis has gotten shorter. It's compressed. Everything below the neutral axis has stretched out. It's gotten longer. And that's how beams deform, okay? Make sense? All right. So let's do a little bit of geometry. I propose that in its deflected shape, we can express that length, that L, as this angle of rotation times rho, the radius of curvature. All right? Make sense? Okay. Now that's the length. This dashed line, I'm going to call that a new length. We'll call that L prime. Well, how am I going to determine that? Well, it's still a radius times an angle, right? But the radius is different. Instead of it being rho, it's going to be rho minus however far we are from the centroid, this y distance. All right? Make sense? So do a little bit of, you know, multiplying that out, I get rho theta minus y theta. Any questions? All right. So this is my original length. This is my new length. So how do I find the change in length? Well, it's the new length minus the old length. So I've got L, I got L prime. Subtract those out, I get delta L, which is L prime minus L. Do the math, and it comes out negative. It's a negative y times theta, times that angle. Why does that matter? Well, I want to look at strain. How do we calculate strain? Change in length over the original length, right? So the original length is L. The change in length is this delta L, L prime minus L, right? So plug it out, check it out. You see that the thetas cancel, and I get negative y divided by that radius rho. Sound good? Not too bad, right? Okay. Now, so what I propose to you is that based on those assumptions, the strain is linear, okay? You know, from the centroid, you think y equals mx plus b. In this case, we're doing, my plus b. The slope of that line is just, 1 over this rho. The strain along that depth is linear. So if the strain's linear, I can assume that the stress is linear. E times the strain, and I get this. Now that should be a fairly reasonable thing to state, because if I go back a little bit, I mean, we've known for a while that bending stress is linear, right? Well, that's basically what we've got. Although instead of saying sigma equals my over I, we've now got E times y over rho. Because now we're relating that stress to its strain. We're trying to make that connection between applied loads and resulting deformations. Okay? Sound good? All right. Now, so here's our bending stress profile, which has got to be pretty straightforward from, so far. We've got the neutral axis. We've got where the centroid is. That's probably somewhere about right here. At the centroid, again, is where there's no bending stress. Which, think about that. I mean, doesn't that make sense when you connect it to what we just said with our deformation? I mean, right here is the point of zero stress. It's also the point where the length didn't change, right? If there's no load, there shouldn't be any change in length, right? Right? I mean, here's this table. If I don't push on it, it's not going to form, right? Make sense? So it all kind of connects. Okay. So I want to relate this deformation to the moment. So how can I get the moment in that shape? Well, I propose that I integrate sigma times y. I take a little bit of a differential slice. I take some slice right here. Cut that out. And I'll say, all right, what's the force on that slice? Well, it's the stress, sigma, times the area. And I say, well, what's the moment? Well, it's that force times the distance, which is y. That'll give me the moment in that little slice. If I integrate, that'll give me the moment across the whole section. Now, I got a negative sign in there. Where's the negative sign come from? It comes from our sign convention that we use for bending moment diagrams. When we say smiley face positive, frowny face negative, we're technically going against the right-hand rule. Remember, that for your moments from statics. So I got to throw a negative in there to make everything make sense. All right. Sound good? All right. So let's do a little bit of plug and chug. I've got this sigma term here, which I've already solved for that. That's this. Sigma equals negative EY over rho. Plug that in, so negative sigma y, negative EY over rho. So the negatives cancel out, and I've got this. Now, if I factor out the E and the rho, I've got this. E over rho times the integral of y squared dA. Y'all ought to recognize that, right? That's a moment of inertia, right? I mean, think about it. Remember when we originally talked about moment of inertia, and one of the first examples that we talked about were wooden joists supporting, let's say, an outside deck or porch or something like that. Remember, you take those joists and you face them up like that, right? As opposed to like that. Why? Because they're stronger in this direction. Now, stronger is a word I use very loosely. What I really should say is that they're stiffer in this direction. And by that, I mean they don't deflect as much. So it makes sense then that the moment of inertia should pop up when we're talking about deflections, right? Makes sense. So there it is. So instead of moment equals E over rho times that integral. It's just E over rho times I times the moment of inertia. So I can solve and I can say 1 over rho is m over EI. So this gives us a fundamental relationship between moment and curvature. Remember that rho was that radius of curvature, right? Remember that? Now, you all have had calculus. It might have been a while, and it might have been something that you mentioned in a very cursory fashion when you take calculus. But one of the things that you talk about in calculus is how to compute curvature, okay? Now, this isn't the same thing as concavity, okay? You all talk about slopes and concavity, and that's probably something that sticks in your head a little bit more. For instance, how do you compute the slope of a curve? You take the derivative. How do you compute the concavity of a curve? You take the second derivative. So you all probably remember that a whole lot more readily than you do curvature. Curvature, the formula is a little more intricate. But, I mean, you can open up any calculus book and I'll promise you it's there. To determine the curvature of a given function, y, or f of x, whatever, to determine the curvature, you take the second derivative and you divide it by the quantity of 1 plus the first derivative squared, and you raise all that to the 3/2. And that'll give you the curvature of a given function. Now, what I want to do is talk about the physics of what that means. We're talking about the curvature of beams, okay? We're talking about beams that deflect very small amounts. I mean, we're talking about, beams that are 30, 40 feet long and are deflecting half an inch, an inch. Really small amounts of deflection. So think about this. If I have deflection values that are really, really small, we're talking about slopes that are really, really, really small, okay? So this dy dx is the slope. Now, if I take a really, really small number and I square it, I get a really, 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 really small number, right? So I propose that everything inside this bracket, 1 plus this pile of junk squared, I propose that this pile of junk squared pretty much tends to 0. It gets so small that we can pretty much say that's 0. All right? And if I take 1 plus 0, which is 1, and I take 1 and I raise it to the 3/2, what do I get? 1. 1 raised to any power is 1. So this curvature term, we call that kappa, I can say, let's just say that that's about the second derivative. All right? Make sense? So if 1 over rho is m over EI, and 1 over rho is basically the second derivative of deflection, I arrive at that. That is one of the most fundamental equations in all of mechanics, okay? How many of you are in fluids right now, or have taken fluids? Anybody taking fluids right now? When you do, you will learn of an equation called Bernoulli's equation. That's one of the most fundamental equations in all of fluid mechanics. This is one of the most fundamental equations in all of solid mechanics. It's just all over the place. The relationship between moment and curvature. You might call this, you might hear it called the Euler-Bernoulli beam bending equation. You might hear it called the differential equation for deflection, the governing Diffie-Q. Moment curvature. It has a number of names. In the end, it's all the same thing. Again, this is one of the most fundamental equations that we see. Any questions? Now, this is a differential equation because I have an equation and there's calculus in it. And I swear to you, I took, Diffie-Q and I took grad level math classes, and, if you ask me what is the definition of a Diffie-Q, an equation that has calculus in it. I'm not even making that up. I think that's about as simple as it gets. If it's an equation and it's got integrals or derivatives in it or limits, it's a Diffie-Q. Okay. So one of the things I do want to just lightly stress, and I'd argue I probably emphasize this a little more when we do structural analysis, but you can take this Diffie-Q and connect deflections all the way to loads, pretty straightforwardly, because let's say y is our deflection, y of x. If I take the derivative of that, that is slope, right? I take the second derivative of that, I'm basically saying that's curvature. Now, if I multiply that second derivative times EI, I get moment, right? Now, if I take the derivative of moment, Remember, the derivative of moment is shear. That's how we drew shear and moment diagrams. If I take the derivative of that, I get the loads. So you can actually go from loads to deflections, pretty connectively. It is technically a fourth order Diffie-Q because you take the derivative of deflection 4 times and then multiply it times EI, and that'll give you the loads. But in the end, it works. Any questions? Okay. Now, like I said, this is not Diffie-Q. We are not going to throw in any Laplace transforms or Fourier series or anything like that. Here's my equation. All right? So if I want to solve for y, it is a second derivative. I propose that I just integrate twice. That's it. Okay? So this is the first and most fundamental method of beam deflection solutions, is double integration or direct integration. Now, I'm not going to lie. There are a number of beam deflection methods. As civil engineers, I'm going to show you much more involved methods and much more diverse methods later when you take structural analysis. As for mechanical engineers, I believe you need a fundamental understanding of beam deflections, but I'm not going to spend all semester on it. Okay? So this is one that will work for fairly basic loading situations. Sound good? Any questions? Now, here's the rub when you do this. Okay? When I indefinitely integrate, all right, let's think about it like this. What is the derivative of x squared? The derivative. 2x. Now, what is the indefinite integral of 2x? Well, but what's missing? Plus c. Right there. Remember that? Remember, if you indefinitely integrate, you get some response plus c. Because if I go and take the derivative of that, I get my resulting function plus 0. Right? So I'm going to have unknown constants. And anybody who's taken Diffie-Q knows that pops up. Yep. You have unknown constants. Anytime that you solve a differential equation, you're going to have arbitrary constants that show up in your solution. Now, how do you solve for those constants? Anybody that's had Diffie-Q? Like if you want a number for those constants, instead of C1, C2, C3, what if you want 4? What if you want 5? How do you get those constants? Well, you're on the right track, actually. You're really right there. Say it again. Boundary conditions. You need some boundary conditions for your solution. Now, when you take Diffie-Q, boundary conditions are just some arbitrary notion, just the function at 0 equals 4, plug and chug. And then that's all there is to it. Okay? In here, our boundary conditions have meaning. They have a physical relationship. And it's pretty easy to determine what those boundary conditions are if you look at deflections. So here's some ideas. Okay? So I'm more interested in cases 1, 2, and 3. This would be more for my structural analysis folks, and I'm not worried about that for you all. Let's look at 1 and 2. If I have a simply supported beam, and whether or not I'm looking at a hinge support or a roller support, I take loads and I apply it to that beam, it deforms in some fashion, right? What do I know about the deflection at that support? It's 0, right? Right here, there's no deflection. So there's a boundary condition. The deflection at this support is 0. Bam, there's one of them. Make sense? Okay, what about this? This is a fixed support. This one's a little different. Instead of just deflection being 0, I propose that the slope is 0 as well. Here's my deflected shape, and look, not only it doesn't move up or down, but what's my slope right there? 0. So there's your boundary conditions. Make sense? Any questions? All right. Now, the only other thing that I want to illustrate is units, okay? Now, if you're dealing in metric, this is fairly easy to deal with. As long as you got all your prefixes taken care of, the units kind of wash out. In US units, I think the units can be a little more complicated, but this is where conversion factors come into play. And I've derived a couple for you that I think will make your life a little easier. All right, so your typical expressions for deflection will look something like this. For deflection, it'll be m over EI times L squared. Because think, you're taking m over EI and you're integrating twice. So integrating once would give you a length unit. Integrating twice would give you a length squared. Does that make sense? So regardless of if you're dealing with point loads or distributed loads or what have you, your deflection tends to come out in ml squared over EI. That it tends to come out something like that. Okay, now let's take a look at those units. Well, moments tend to be in foot kips, right? Member lengths tend to be in feet. All right, now if I take an E, which is in KSI, and inches, or moment of inertia, which is in inches to the fourth, and I start chugging it out, what happens? Well, I get foot kips times feet squared, kips per inches squared times inches to the fourth. Carry everything out. My kips cancel, and I get this. Okay? Am I really going to say that my beam deflects, 4 feet cubed over inches squared? That doesn't really make a lot of sense. I'm trying to determine how much this beam deflects. What do you think would be an appropriate unit for expressing how much a beam deflects? Maybe inches, right? Make sense? Now that's deflection. Rotation, instead of being ml squared over EI, it's ml over EI. So you look at this, it's another little quandary. It comes out feet squared per inches squared. So if I get all my units right, rotation actually comes out unitless because it probably comes out in something like, radians, right? Now, beam rotations are kind of small, so I like expressing them in degrees so that the numbers, I think, make a little more sense to me. All right, so here's what's happening. So my units come out for deflection in feet cubed over inches squared. This is feet squared over inches squared. So I'm going to throw in a conversion. For the deflection, I'm going to say, all right, feet cubed per inches squared. If I can turn this into inches cubed, it'll come out in inches. Make sense? So feet cubed, I need to turn that into inches cubed, so my conversion factor is 12, right? But I got to cube it. So 12 times 12 is 144 times another 12 comes out to be 1728, okay? For rotation, instead of it being 1728, it's 144 because I'm only doing 12 squared, not 12 cubed. But if I want to get everything in degrees instead of radians, I got to convert by doing 180 over pi. So this right here, this is my conversion factor for deflection and rotation, respectively. So if I just plug and chug and multiply my answer by 1728 for deflections, it'll come out in inches. If I plug and chug for rotation, in this, it'll come out in degrees. Yes, sir? Yes?
The y units is ml squared over EI. How come they'll divide by 2?
No, I'm talking about units. I'm just talking about units. Oh, okay. Yeah, this is just the units now. So I'm saying if I've got m over EI and I'm integrating twice, whatever the function is, I'm going to get some m times some length squared. I'm not saying that the integral of this is x and then x squared. I'm not talking about a specific function. I'm just talking about the units that you get as a result. And they tend to come out something like that. And this is true if you're dealing with point loads, distributed loads, fixed beams, simply supported. It's all the same. Whew. Any questions? Everybody good? Okay. So I do apologize in advance for the alphabet soup that is to result from this example, but I think it's kind of important just so you all understand where the formulas come from that you're going to use later. Okay? All right. So we have a beam that's simply supported and it's subjected to a uniformly distributed load. This is one of, if not the most fundamental beam deflection formula that there is, period. Because this is a simply supported beam subjected to a uniformly distributed load. I propose every beam in existence is being subjected to a uniformly distributed load. Why is that? What load must all beams be able to withstand? Gravity. What do you mean by gravity? Their own self-weight. Okay? And 99 times out of 100, unless you've got a beam that has some really changing cross-sectional properties, a beam weight is idealized as a uniformly distributed load. So this is one of, if not the most fundamental beam loading scenarios that there is. Okay? Now, we're going to derive a formula, and then we're going to determine the maximum slope and deflection due to these formulas. Okay? Now, just so we're all clear and paying attention, I propose that the beam deflection looks something about like that, right? My arc's off a little bit, but bear with me. So let's talk about a couple things. Number one, what are my boundary conditions going to be? I'm going to have two of them. Now, I'm going to have two of them that I need because I'm going to integrate twice. So I'm going to get two unknown constants. I propose that the deflection here is 0 and the deflection there is 0. Those are my two boundary conditions. Make sense? All right, that's point one. Point two, where's maximum deflection going to occur? L over 2, right smack dab in the middle. Where is the maximum slope going to occur? I propose the maximum slope is here, here, and here. Right there. They're going to be equal and opposite, right? This slope's going to be going down, that slope's going to be going up. Forgive my artwork. It's about the best I can do. Be maximum, yes. We're here. Let's do this. How about that? Looking at that one.
Is the slope of B affected assuming B was a point support, like a rocker support? Is it affected by the fact that A can't slope?
Yeah, I guess it is. But okay, so the question was, would the slope at B change if there was a roller here? The answer is yes. But this would also be an indeterminate structure because I would have too many reactions than I would equations of equilibrium. Can we handle that? Yeah, but you've got to use some additional methods. And I don't want to get into those methods because it goes beyond what we need to do in here, but I will simplify them by saying this. If you had a roller right here, you would have one too many unknowns. So what you have to do is you have to pick one of those unknowns as a redundant. Okay, so let's say the roller is the redundant. And I solve for this structure by recognizing that if I have a roller right here, what's the deflection? 0. So I end up doing two analyses, one with the roller gone and one with the roller there. And I say, all right, I've got, if the roller's gone, it's going to deflect down. Then I ask myself, well, how much load do I have to place up so that it deflects upward? And that's the reaction. Now, for a case like this, it'd be simple. It'd be 10 kips. But if the load was over here, it wouldn't be so straightforward. Sound good? All right. I didn't even open my notebook. Excuse me. Once it decides to open. Okay. 61 pages. All right. Now, I changed the pen, I think, since last time. So it looks a little thinner. So you all let me know if you can't read it. So we're on example. What number is this? 25. We are trucking. All right. So here's the beam. All right, we have a roller or simple support right here and a simple support right here. And in all honesty, the hinge and roller doesn't really affect what we're talking about. Like, I could flip them and it wouldn't change the answer. All right. Okay, now this is a load W. Now, it's pressing down on the beam. I'm going to take a wild guess and say that the reactions are going up, right? You've got a reaction here and a reaction here. All right. So let's see. Let's call this BY. Let's call this AY. Can y'all read that? Okay, all right. Now, a couple things I'm going to do that I haven't done in previous problems is, for one, I'm going to define a coordinate system. So I'm going to say that here's my x-axis and here's my y-axis. Okay? That's point one. Now, go ahead and do this. The beam is L long. All right. Help me out. Let's do this like we would any problem. I have a distributed load. I can collapse that into a single point load, right? Which is going to be what? It's going to be in the middle, and what's that magnitude going to be? There we go. Right? That's A, that's B. So, what do you think? Would it make sense then that AY is WL over 2? This is WL over 2. Does that make sense? Sound good? I mean, do we need to go through and do the statics, or are you all just okay with that? Sound good? Okay. Now, what I'm going to do is I'm going to do something a little differently that I've done in problems before. And that's I'm going to cut a section and try and derive an equation for a moment. Now, before I do that, let's just make sure we're aware of what would go on from a shear and moment diagram perspective. Would you agree that the shear diagram is probably going to look something like this? It's going to go up, it's going to go down, and it's going to go up, something about like that, right? So this is L over 2, this is L over 2, this is WL over 2, that is minus WL over 2, and this is shear. Now, what the heck? Let's go through and draw it out. So, how do we draw the moment diagram? We integrate, right? So what's the area under this triangle? Well, it's 1/2 of that times that, right? So what is that? 1/2 of WL over 2 times L over 2. Maybe it's WL squared over 8. Make sense? This is going to be minus WL squared over 8. So, if I draw the moment function, let's be clear. Lot to a little, little to a lot. I propose that your moment diagram looks something about like this. Everybody okay with that? It's not very complicated, is it? Okay. Now, in order to do this, though, I need a moment function. I need, m of x. I need a moment function. So in order to do that, I'm going to cut a section. But before I do that, let's look at the math. The moment function, should that be a line, parabola? What should it look like? Parabola. It's a negative parabola, so the x squared term should be negative, right? Let's see if that happens. All right. So, let's go up here, and let's cut a section at some distance, x. All right. What do we have? I have this. I have that. Cut a section. And I've got this. So this is WL over 2. This distance is x. And this is W. Now, I can take that distributed load, collapse it into a single point load. Now, what's the magnitude of that point load going to be? W times X. And how far is it going to be from the cut? There we go. Sound good? Now remember, anytime you make a cut, there's going to be an unknown shear and an unknown moment. Sound good? Let's do both of them, just for the sheer heck of it. No pun intended. I know. It's tough, isn't it? So let's sum forces in the y direction. So we're looking at this free body diagram right here. So what do I have? Bless you. What do I have? Going up, I've got WL over 2. What do I have going down? I got W times X, and I got V. And if you want, you can think V of X. That's fine. It doesn't matter. So I propose that's your shear equation, right? Moments. Let's sum moments. In this case, let's sum moments at the cut. All right? So I'm at the cut. All right? So WL over 2, that causes moment, right? What's my moment arm? X. Which side, left or right? All right? Okay. What else? Well, I've got WX, right? Acting at a moment arm of X over 2. That's going to be on that side. And then I got what? M? Does the V cause any moment? Not at the cut, right? It's right there. So I got or what do we think? So far, so good? Now, let's dissect these a little bit. First off, let's look at that shear equation by itself, the one in red. What is that the equation of? Looks to me like the equation of the line. Y equals mx plus b. What is our y-intercept in that line? WL over 2, right? Let's look at the graph of the shear diagram, right? Let's look at this. Remember, in this graph, that's the x-axis, and that's the y-axis. So what is the y-intercept on that graph? Looks to me like it's WL over 2, right? Now, does that line have a positive slope or does it have a negative slope? Negative slope, right? What is the slope of that line? Negative W. The slope of the shear diagram is equal to the load. The load's W, it's going down, so it's negative. Slope's negative. Let's look at the moment. What is that the equation of? Well, if I had to guess, it looks to me like it's the equation of a parabola, right? And you said it was a negative parabola, that the x squared term would be negative. What happens if you plug in x equals 0? What do you get? Right here. That's what the moment is right there, isn't it? What happens if you plug in x equals L? You get WL squared over 2 minus WL squared over 2. You get, which is what's right there. What happens if you plug in x equals L over 2? You get WL over 2 times L over 2. This is WL squared over 4 minus W over 2, WL squared over 8. So WL squared over 4 minus WL squared over 8. What's 1/4 minus 1/8? WL squared over 8. Right there. The big one. What is the derivative of that? What is the derivative of that? Negative WX, right? Because this is 2x, 2x over 2. What is that? Looks to me like the derivative of this is that. True, but okay, that's a good question. Could you just integrate the shear diagram or integrate this to get moment directly? Yes, you could. Here's the rub though. What is the integral of this? Let's imagine we didn't know what the heck was going on here. Well, WL over 2 times x, right? Minus WX squared over 2 plus c. There's a constant there. Now, you would solve for that constant by recognizing this is a simple support, so the moment here is 0. Yes, that's a good question. Both of these functions are valid from x equals 0 to x equals L. Okay? And that's a good point. If you have a beam where you have different loading conditions, like let's say you have a beam with a point load in the middle instead of a distributed load, then you got to have two moment functions, one from 0 to L over 2 and one from L over 2 to L. So, and that's where methods like this get a little tougher. So, all right? So yeah, you would have to use some sort of boundary condition to solve for that constant C. And we're dealing with a simply supported structure. If we had a cantilevered beam, that boundary condition would be different. So it's easier to just do this and then check if your values make sense. Any questions? Everybody good? Okay. All right. Has everybody got all this? Okay, let me go on to the next one. I said let me go on to the next one. There we go. Okay. So, we're going to do double integration. All right. So, our moment function, just to rewrite that, is this. All right. So, here's our moment function. We need to integrate twice, okay? So, let me sort of over here on the side do a little bit of this math. So, m over EI equals, I don't know why I did that backwards, but equals the second derivative. If you want, you can say y double prime if you're being lazy. Okay? So would you agree that EI y double prime equals m? Would you agree with that? Just multiply that over. And if I integrate, I would get EI y prime is the integral of m dx. Everybody okay with that? Now, y prime, we have a very special name for that. That is the slope, okay? So I propose to you that we can say, therefore, EI times the slope is the integral of that. Now keep in mind this is double integration, so we're going to integrate twice. Okay. Now, help me out with this. Let's integrate. So WL over 2 times x, what's the integral of that? Well, this is a constant. So what's the integral of x? x squared over 2. So the integral of all of this would be WL over 4 times x squared. That'd be a fair way of saying it. So WL over 4 x squared minus. Now, what's the integral of this? Well, the W over 2 factors out. What's the integral of x squared? X cubed over 3. So, what was that? W over 6 times x squared, or x cubed? What am I missing? Plus c. Now, here's what I'm going to do. I'm going to say plus c 1. And there's a reason why, because I'm going to do this again, and I'm going to get a C2. All right? Sound good? All right. So EI, theta, so on and so forth. Sound good? All right. So there's EI theta. Let's do EIY. So that's the integral of all right. Okay. Let's carry this out. Somebody else. All right. So let's start off with the first term. WL over 4 times x squared. So we factor out the WL over 4. What's the integral of x squared? Somebody else. Somebody. There you go. Exactly right. Because that's x cubed over 3. Multiply that out. WL over 12. X cubed. Very good. Minus. Somebody else. All right. So we got W over 6 times x to the third. So factor out the W over 6. What's the integral of x cubed? X to the third. Well, okay, it's x to the fourth over 4, right? Ignore this one, right? So x to the fourth over 4. So if you've got 4 and 6, it's not over 18, it's over 24. There you go. All right. Plus, now let's think about this. What's the integral of a constant? Constant times x. What am I forgetting? Plus another c. So now you can see why there's a c too. I plan ahead. Did you like the hand motion go well with it too? I plan ahead. Okay. Any questions? This isn't too bad, right? Now, so this is our expression for slope and deflection. We've got that figured out. Now we got to do boundary conditions. All right. Now, how many boundary conditions do we need? 2. Why do we need 2 boundary conditions? Because we have 2 constants. Pretty simple, right? Pretty simple stuff. So, all right. So we got 1, 2. Let's see if we can figure them out. All right. Now, to figure them out, I'm going to go back real quick to the previous slide. Everybody got this? All right. Now, we are trying to solve for the deflection. So it's probably going to deflect something about like that. Are there any points that we know? Any deflection points that we know? A and B. And what do we know about those points? What is 0? Deflection is 0. We know that y equals 0 here and here, right? Now we got to get a little bit more mathematical about it. What are the coordinates of x right here? 0. What are the coordinates of x right here? L. There we go. There we go. So here are my 2 boundary conditions. All right? At x equals 0, y equals 0. At x equals L, y equals 0. Those are specific for this problem. That can change looking at a different problem. Make sense? All right. Let's take care of these one at a time. All right. We'll probably hit this problem up sooner or when we come back because I think we're going to run out of time. Let's see what we can come up with. Let's deal with the first one. All right. So we have this equation, EI times Y equals WL over 12 x to the third minus W over 24 x to the fourth plus C1x plus C2, right? The first boundary condition says that when x equals 0, y equals 0. So I'm just going to plug and chug. So EI times y, what is y? 0 equals WL over 12 times 0 cubed, right? Minus W over 24 times 0 to the fourth plus C1 times 0 plus C2. What does that tell us? Simple one, right? You know what? We're starting to hit that time. So the next one, dun, 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 to be continued. We're running out of time, and I don't want to rush this. So has everybody understood what's going on so far? This isn't that bad, is it? And hopefully this brings a little bit more of the reality into that boundary condition stuff you learn in DiffEQ, right? Now there's actually a reason for it. Now, in the world of engineering, there are two types of those conditions. There are boundary conditions, which are related to position, and then there are initial conditions, bless you, which are related to time.
Well, not having had DiffEQ hurt me.
No. It'll supplement what you learn later. All right. That's all I got. I will see you all on Thursday. Remember, your homework's due. Any quick questions about that before we end? All right. You will get a solution on Thursday, and I will give handouts on Thursday for the exam. All right? That's all I got. We'll see you on Thursday.